Hello and welcome to today's webinar. On behalf of Drug Target Review and Eurofins Pharma Discovery Services, I'd like to thank you all for attending. I'm your moderator, Mike Stones, Managing Editor of Drug Target Review. Today's speaker will be Arsenio Nueda, Head of Molecular Biology at Almirall. Following his presentations, we'll move into a live question and answer session where you can pose questions to today's speaker. And please remember, you can submit questions at any point during the webinar using the Ask a Question panel situated below the player. So let's hand over to today's keynote speaker, Arsenio Nueda.
Okay, thank you very much. And I would like to thank Drug Target Review and Eurofins DiscoverX for organizing this webinar. So I'm glad that we have the opportunity to talk about our work here today. And so I will go into the presentation. And as I would like to first mention that this work has been recently published in PLOS 1 this last January. So in case you want any additional details on any of the things I'm going to talk about, you can go to the paper. The paper is referenced at the end of the presentation and get more details on all the subjects that I'll be touching on. What I'm going to talk to you about today is our experience using bioactivity profiling to progress phenotypic hits and how we can benefit from those really powerful tools to optimize the process, particularly for phenotypic hits, and to take advantage also of complementary tools like reference molecules or referent drugs that you would be seeing examples of this. We, as you probably know, bioactivity profiling has been traditionally used to assess the selectivity of drug candidates in conventional target-based screening approaches, where pharmacological selectivity is a key requirement from the start. So for this type of target-based assays, a target is identified, and then this is what the primary screen or the high-throughput screening is organized around, so that everything is focused in a single target approach. But still, these profiling tools are needed afterwards to make sure that the molecules that are being generated maintain the necessary selectivity. So in contrast to this, and I would rather say complementary to this, phenotypic screening provides hit molecules with the only initial requirement of activity in a functional assay. This may mean modulating a single target or several targets, depending obviously on the molecule and the assay. And also, in this case, subsequent progression of the hits requires profiling, I would say, for different reasons. In phenotypic screening, even though we may not predetermine the target that the molecule will be done modulating, we would like to know what targets are being modulated by our hit molecules for different reasons. So you probably know that this is not even a regulatory requirement to be completely selected for a target, but for safety reasons, and as I will show you today in the next few slides, in order to optimize the molecules and to take advantage of the handles that will most benefit the optimization of the molecules. So we really need or use this, like I said, powerful profiling tools for the benefit of progression and a well-defined molecule that we can really move on to development later on. As I mentioned, here you can see in blue at the top left, traditional relevant or target-based approach, which is a disease-relevant target in this case, which we may have obtained using evidence from academic work, from target validation work, whatever evidence that we can use to define that target. And the complementary approach would be the approach used in phenotypic screening, where we are open to having, as I mentioned, a single target or several targets even in a polypharmacology approach, in order to modulate the disease-relevant phenotype for improving the disease symptom or indication symptom. So this concept is important, so we have to know that in principle it should not be a problem to have several targets, but we will have to find a way to optimize our molecules under those conditions. Okay, this is showing how both paths, both the target and the phenotypic-based drug discovery pathways, I could say, are completely complementary. So if you can see at the left-hand side that we can use cell-based model systems either to validate our targets for a target-based approach, or as the models where we will be running our phenotypic screen, and so the same tool, as you can see, can be used for both approaches. And then as we move to the right, as we get to the point where we can get hits on the bottom part, the phenotypic screening hits, we will use biological profiling to get the target fingerprint of those hits. And from this target fingerprint, we can infer a target that may be of interest for new programs, or target-based programs, or a target that can be used for the optimization, for the additional optimization of these hits alone, or in parallel with phenotype-based optimization. So we can follow all three different ways, like I said, for the benefit of the drug discovery process, and in a very complementary way. I insist on this because in the early days of phenotypic screening, me and others were trying to convince colleagues that this type of approach was worth the effort. It seemed that people were seeing this as a completely different and even antagonistic approach compared to target-based screen, but there is this is absolutely not the case. These two approaches complement each other, and you can use common tools and then divert from one to the other along the drug discovery process. So in the next slide, I will give you a very brief introduction to the specific target, the specific phenotypic endpoint and target that we used, and this was TSLP, which is a mediator, an inflammatory mediator, which has been linked to allergy, to asthma, to atopic dermatitis, and is produced by epithelial cells, by mast cells, and this mediator regulates T cells, particularly the Th2 type cells, and has been linked to the atopic march and to asthma in particular. So we were interested in working with this and finding ways to downregulate this mediator in order to address asthma, specifically through the Th2 pathway. And as you can see in these color boxes, we had different options at the time. We chose to inhibit the production of TSLP as a phenotype, but we could have selected to block the interaction of TSLP with its receptor, or to block the signaling pathways that the receptor engagement was resulting in. So all these options were valid, and we just made the decision that we would be trying to look for more opportunities or new opportunities for drug discovery to find drug discovery leads using the phenotypic approach. But the basic concept, TSLP is a target, so the basic concept is really using a phenotypic readout to find inhibitors of a target that was relevant in this case in the context of asthma. So I will briefly explain our system model, our cell-based model, which is a critical part in phenotypic screening to find the most relevant model that we could use to recapitulate the relevant endpoints of the indication, and that at the same time is good enough for to screen a library of small molecules. And in this case, this is obviously a balance. The perfect model, as you know, is the human, but we need to find. At the time we decided to use human primary cells derived from donors, from 2 donors specifically, and as a approach that we believe was close enough to the problem or the endpoint that we wanted to look at. So in this case, these were standard donors from commercial origin. We obtained these cells from Lonza, actually, and these donors 1 and 2 were used at different stages during the phenotypic screening process, and we obviously verified that they were producing the TSLP mediator in both cases. Also, the isoform that we want, there are 2 isoforms of TSLP, a long and a short form. So the relevant form in this case is the long form, and so we checked that. And we used a relevant stimulus in this case, which is poly-IC IL-4 mimicking allergen viral insult to the lung tissue. So these were healthy cells, and on the chemical spaced part, so the molecules or the library that we use, we combined with this model, was a library of close to 50,000 compounds, a subset of our in-house library. These were 384 well plates, so we had 144 plates to test, and these plates were selected. We didn't pick compound by compound, but we selected plates based on enrichment in compounds having the 4 criteria that are listed here. Structural diversity, this was very important for us. However, as you may understand, this library was not really designed for phenotypic screening at that time, and it was enriched in molecules that were targeting GPCRs, kinases, so many of the programs that had been run in the company, but still we tried to get the most diverse set possible from the library. So we also looked for low predicted cytotoxicity, obviously physicochemical properties compatible with crossing the cellular membrane. We were interested in intracellular targets, and also lack of structural alerts as judged by the chemists. So one key point or one learning point from this structural diversity approach is that I think this is what is going to limit the output of the phenotypic screen in the end. So if we really want to get the best out of our phenotypic system, I really believe we would need to be or to try to get the most diverse collection of molecules possible. Because as you will see when I show the results, probably many of the things that we showed were limited or were based on the origin of the molecules. As I said, many of them designed for kinase and GPCR programs, and also there was a set of molecules which came from outside sources, which also popped up during the screen. What we did was to combine these 2, I like to call them axes, the chemical space axis, the chemical universe of molecules, and the phenotypic space axis. In the phenotypic part, you can visualize here something that was described several years ago by Fabian Bissan and colleagues in the literature, which was the rule of 3 for phenotypic screening, which is relevant or as relevant as possible cell-based systems, which is the NH, the normal hemo bronchial epithelial cells shown here, and the relevant stimulus, a poly-IC IL-4 stimulus, recapitulating viral insult and allergen insult, and also relevant phenotype, which is the production of TSLP. So we were trying to mimic as much as possible with the obvious limitations of high throughput screening or medium throughput screening, these 3 basic rules. And what we got, we did this primary screen using human donor number 1, and these bronchial epithelial cells, or primary bronchial epithelial cells that we use for the primary screen. Then we did a confirmatory screen using both donors 1 and 2, also a validation using qPCR to use a completely alternative strategy or technology to validate the hits. So what we got in the end was the chemistry and the biology, which represents the biological and chemical starting points, which I will be talking about in the next few slides. We started off from 45,000 compounds, as mentioned. With the cutoff point that we established for inhibition, which was 45%, we obtained about 2,000 actives in the primary screen. And among these, and interestingly, some of them were actually enhancing or upregulating the expression of TSLP, which was interesting for us, and so we kept them for subsequent filtering steps. From those 2,000, close to 2,000 compounds, we did the screen, as I said, using cells from donor 1 and donor 2, and we managed to confirm for close to 500 molecules for donor 1, 160 for donor 2, and also we confirmed some of the molecules upregulating TSLP. And very interestingly, there was a lot of coincidence between the 2 donors. So of this list of 400 and 160, the 80 most potent hits, which were coincident, 77, or the 88 most potent, the 80 most potent hits, 77 were coincident between donor 1 and 2. So we were happy to see that, and happy that we were having this coherent reproducibility of actives between one and the other. So we applied the obvious filters of viability, cytotoxicity, and assay interference, and finalized obtaining a list of close to 100 hits. These 100 hits, we then did dose response with each of them, and a qPCR validation. qPCR validated most of them, and with dose response, the list went down to 86 hits. And still we had one which was regulating TSLP, which was very, very attractive for us. Not because it was the purpose of the screen, but because it would be revealing. We think that it may be a good tool in the future to reveal biology, as you will see. So we have here the general view of the 7 molecules that we selected as representative molecules of this 86 hit list. And these were in 3 categories. So the molecule on the left, number 1, upregulating TSLP. This is shown as a percentage. And upregulation in the middle, we have the activity of the hits that were derived from our internal chemistry, are actually kinase programs, P38 and SYK kinase programs. You can see the IC50 for TSLP inhibition. This is 22 nanomolar, 75 nanomolar, and 170 nanomolar. So the compound number 2 and 3 are from a P38 program, compound number 4 from a SIG program. And to the right, these are the external hits, the hits that we obtain from external sources. Number 5 was a JAK inhibitor, actually described as a JAK inhibitor, as you will see, is a multikinase inhibitor. Owabain is a well-known sodium-potassium pathway inhibitor blocker. Nocodazole, which we really didn't like very much, but we wanted to keep the structure for the purpose of keeping diversity and getting as much information as possible. And number 6 was a compound that was actually described as an inducer of apoptosis, but still, this is something we will comment about later on. We decided to keep also this compound because there is always the possibility of separating the activity we are looking at, in this case TSLP downregulation, from other non-desired activities during optimization. So for those of you working in drug discovery, you may be familiar with this concept. We can see that compound number 1 not only upregulates TSLP protein, but also regulates mRNA synthesis, and this is very consistent. And we actually did not characterize this compound any further, but we would consider this our first biological starting point, not a compound that we would optimize, obviously, in the context of the program, but a compound that we may use to get information, biological information, based on this interesting capability to induce the expression of TSLP. We did run some in silico predictions and looked at some of the targets that came out of that, but we didn't do any profiling. But still, as I say, I think this can be a very useful tool for people studying TSLP biology. This summarizes the process that we followed, the logical process that we followed to profile and to optimize these molecules and try to map the activities that we were seeing during this process. So to begin with, the hit validation and characterization that was based on the chemotype, and see for the in-house compounds derived from kinase programs, compounds 2, 3, and 4. We obviously had a lot of information available for those compounds. 2 and 3 we knew they were really optimized compounds. And you can see the activity they inhibit TSLP on the left-hand side, mRNA downregulation, second column, and the second column from the right, you can see inhibition of a biochemical assay, P38, and SIG. P38 compounds are even less than 1 nanomolar in the case of compound 2, and 2.8 nanomolar for P38, so that's quite a potent IC50. And this translated in an activity in a cell-based assay measuring indirectly P38, also in quite potent activities, as you can see. Compound number 4 is a compound that, even though it came from a SIG program, it is inactive in SIG, so obviously it was a compound that had been ruled out in the context of the program because the IC50 was close to 12 micromolar for SIG. Still, it showed activity in a THP1 assay looking at PI3K dependent activity, so we knew it was active in a cellular context. And so we thought it was interesting to really look what was behind this TSLP activity, which appeared to be more potent than the PI3K activity. For the external hits, you can see activities in TSLP, which span from 16 nanomolar for Wabain to close to 1 micromolar for Nocodazole. Inhibition of mRNA is also shown, and confirming the activity, as I said before, using a different technology. And for compound number 5, we realized it was also a SIG inhibitor, 58 nanomolar IC50, and obviously a JAK inhibitor, which was how the compound had been described. The compound number 5 was active in cell-based assays, looking into SIG and STAT6 JAK-dependent activity in RA1 cells, which is actually this is an IL-4 dependent activity. So this was something expected. So the activities reported for the other compounds were for bovine, as I said, is sodium potassium ATPase. It is also been described as an NF-kappa B inhibitor. Meclobazole, in addition to being a tubulin polymerization inhibitor, is also been described as an ABL phosphorylation inhibitor. And for compound number 6, the only information we had was it was an inducer of caspase activation. So next slide. We went on to profile the in-house compounds and together, the in-house compounds together with compound number 5, so the kinase inhibitors in this case. And for this, we started off using a kinase selectivity panel. And in this case, what we were thinking was to get a first target fingerprint. So we would be looking into the target fingerprint, looking for an initial view of the potential mechanism of action in order to pinpoint the targets that may be involved in the regulation on the blocking of the phenotype. So as you can see, this is a general view of the panel. I have split this in 2 slides for convenience. And as you can see, we tested this in for compounds 2, 3, 4, compound 5, and also compound 7, which was an internal reference compound, also a p38 inhibitor. And this was tested in a 125 kinase selectivity panel at a concentration of 10 micromolar. So activity shown here is percentage of control activity in the absence of inhibitor. What we can see is the high selectivity of compounds 2 and 3, which is expected, being very highly optimized compounds, which were obtained in the context of a program. The only, for example, for compound 2, the only other activities that you see is MKK6, which this is actually because p38 is used in this assay, and also TRKB kinase. So the other thing that we see is, or the only other activity that we see, for example, for compound 2 is TRKB, and this is not the case for compound 3. Compound 4 was somewhat less selective. Still, we were only seeing 9 activities out of the 125 activities that were looked at in this panel. And we also realized that at this concentration, compound 5 was poorly selective. Obviously, an inhibitor of JAK and SIG kinases, but selectivity at this concentration was not really good enough. Compound 7 was a structurally different reference compound, and which we used as a tool here, and also very selective, but as you can see, still sufficiently selective that we can compare with compounds 2 and 3. We proceeded to the next step, which would be to try to map the correlation of these activities. For us, at that time, when we had very highly optimized p38 inhibitors, very potent, very selective, we obviously believed that this was obviously dependent on p38 alone, and we decided to check that using these compounds and also compound 7, and you can see compound 7 and tofacitinib, which is a JAK inhibitor. So this would be a way to look at p38 inhibition with alternative chemistry than the structural or the structure in our hits. And surprisingly for us, compound 7 still very potent. You can see highlighted in green, biochemical and cell-based activity. And as you can see, it's quite high, but surprisingly, the inhibition of TSLP or downregulation of TSLP production was relatively poor compared to the potencies that we were getting with the other compounds. Something similar happened with tofacitinib. It is a quite potent JAK inhibitor with potent cell-based activity, but not really. It did not really show a very potent inhibition of TSLP production. If we compare the ratios, the activities of these compounds, you can see how to the right, highlighted in green, we have this cell-based assay, so quite potent compounds. The compounds are going into the cell, and they should be finding their target. And in contrast, the left column, the green, yellow, and red, you can see how they have different levels of cell-based activity, of TSLP, downregulation activity, which does not seem to be very well correlated with the cell-based activity and with the biochemical activity in the middle. So what we concluded from this was that maybe it wasn't P38, at least P38 alone. So we don't think it was just by chance that we got this P38 family of inhibitors in our screen, but probably it was not only the only explanation for the activity that we were seeing, because mainly of the fact that this and in fact other P38 inhibitors that we used did not really show high activity. We, with regard to compound number 4, we decided to further profile it because we were interested in, as I said at the beginning, in new opportunities for inhibition of TSLP. It was a kinase inhibitor, relatively selective, active in a cell-based assay. So we had an idea that it was probably inhibiting PI3 kinases at some level. But very interestingly, it wasn't a Syk inhibitor, and it showed pretty good selectivity. You can see it inhibits 9 of the kinases shown, and this is mainly PI3Ka and tyrosine kinases. So we decided to repeat the cycle of profiling, in this case, going further in depth into this, with this compound, into more comprehensive bioactivity profiling. You can see that what we did with this compound was a biochemical panel, the Bioprint panel. So the biochemical panel, the Bioprint panel, was a general panel with a large number of activities, and gave us the opportunity to compare with an internal database of reference drugs running the same panel, and the BioMAP panel, which I would call it the phenotypic version of bioactivity panels, where we can look at 12 different systems, very interesting, diverse set of human primary-based cultures and co-cultures, which are treated with relevant stimuli, and which give us the opportunity to look for similarities also by looking to a database, similarities to drugs, reference marketed drugs, and other reference compounds. So we can see, we tested compound 4 at a concentration of 1 micromolar, and what we can see is that it was really very selective in the general selectivity panel, which is the first step in the Bioprint, or was the first step in the Bioprint panel. And this shows inhibition of PD5, PD6 at this concentration. And in the next slide, you can see inhibition of the MT3 receptor. So it's only 3 activities that were in a panel of 129 activities. Activity here is shown differently than in the kinase panel. This is shown as percentage inhibition of the activities. So with only these 3 activities, we and the other activities that we had identified in the kinase panel, we decided to run those response curves to determine the IC50 and confirm the data that we get from the panels. As you know, selectivity panels are very informative, but they represent a duplicate from a single concentration point, which in some cases needs to be confirmed to make sure that the activity is really there. And so we confirm from these 10, 12 activities here, between 0 and 5 micromolar. You can see mTOR, PD5, PD6, tyrosine kinases, DNA-PK, DNA-dependent protein kinase, PI3K. And interestingly, TSLP was still the most potent activity that we had for this compound. This was suggestive of, typically when we do a biochemical assay, all these assays were biochemical except TSLP, we tend to get less potency in the cellular version of the same activity. And in this case, still, the TSLP production was, downregulation of TSLP activity was topping the list. And this was indicative for us that we were looking into a scenario where probably more than one activity, more than one biochemical activity was contributing to this TSLP downregulation phenotype that we were seeing. So we can see the comparison that was made between the profile of this 129 profile, this is 3 activities, and the database of reference drugs and marketed molecules, marketed drugs, and no relevant activity was found here. This is 1 micromolar, remember, and it was compared with 2,500 compound database, and the Pearson correlation that was seen was not in any case over 0.5. So with this result, this was somewhat good news for us because the compound was showing good selectivity, but we were a bit disappointed. We did not find really any additional information from this approach, but still the concentration was probably low enough so that we really didn't see a lot of non-specificity. So in the end, probably the result was informative, and I would say that going higher in concentration would have complicated things for us, at least from this point of view. And in any case, we tested the BioMAP, or we tested the molecules were tested in the DiscoverX BioMAP system, and what we saw there, interestingly, this was run at 0.1 micromolar, 0.3, 1, and 3 micromolar. So in this BioMAP system, there are pretty strict criteria for acceptance of activity, and this means dose response, several activities in the dose response, lack of cytotoxicity. This is the general view from a compound in the BioMAP system. And you can see immediately that there are a few, the black arrows represent cytotoxicity. So there is cytotoxicity for the top concentration, 3 micromolar concentration in several systems, particularly in endothelial cells, monocytes, fibroblasts, not in bronchial epithelial cells, which is the systems in the middle, the BF and the BE. And this system is a 12 human primary cell system with, as I mentioned before, physiological and disease-relevant stimuli, which cover a lot of immune-relevant stimuli. And in this case, it was compared with a database. I believe this database is now more than 4,000 compounds. In this case, it was more than 3,000 compounds. We can see the activity in the BioMAP system in the concentrations where there's not such a significant cytotoxicity, still some cytotoxicity in the endothelial cell systems to the left, the extreme left, the 3C system. So this is bracketed. It means it was not taken into account for the analysis, but basically, to summarize, what we got from this panel is immunosuppression type of profile, immunomodulatory remodeling activity, so regulation of IL-17, IL-6 in B cells, PBMCs, upregulation of IL-8 in fibroblasts, and downregulation of IL-10 in the epithelial cells and macrophages. There was some anti-proliferative effect in fibroblasts and also in T cells, and still something that was very interesting to us was the phenotypic selectivity that we were seeing in the systems, which were also very relevant for us. The BF4T and BE3C systems were only 2 of the 32 endpoints which are looked at into these systems were being downregulated. TSLP is not showing up here because it's not measured in this panel. But like I said, this was good to see how there was not such non-specificity or non-specific inhibition of endpoints in these systems. So we can see the matches that we got after the compound Discoverex people looked into the database, and this is what the system returned, and was a similarity with the everolimus, tensirolimus class of compounds. So as an immunosuppressor, it was matching the profile with Pearson correlation of close to 0.8 and a bit more than 0.8 for tensirolimus. And this meant these are selective mTOR inhibitors. So this meant that the compound was behaving as an mTOR inhibitors in these systems, in spite of having up to 12 activities in the 0 to 5 micromolar range. We were seeing it was behaving as an mTOR inhibitor. So and we then decided to verify that mTOR, using reference mTOR inhibitors, that mTOR was behind or was capable in itself of downregulating TSLP. And again, we were mapping activities that we had seen during the profiling, the same way we did map, or we did try to map P38 activity, or the role of P38 activity in the kinase inhibitors before. So what we got here was that everolimus and AZD8055, which are standard mTOR selective inhibitors, those at the cellular and the biochemical level, were in fact and indeed inhibiting or downregulating TSLP quite potently. Still, and we look at mTOR activity, it is in the 1 micromolar range. So we had just confirmed that mTOR was involved in the inhibition of TSLP. We had confirmed that the compound was behaving as an mTOR inhibitor in those cellular systems, but still, this was the activity of mTOR is 10 times less potent than what we were seeing for TSLP. So this was confirming for us that some other activity in this list was probably also contributing to the downregulation of TSLP, which was also very interesting. So what we did then was to do some preliminary heat expansion and optimization approaches to try to get some closely related compounds to and evaluate them in these assays and see how if we could improve activity. This is what you can see here for compound 4 at the top. And remember, it was a TSLP downregulator, didn't inhibit SYK, and it was active in a cell-based assay. And compounds 9, 10, 11, and 12 were closely related compounds that we had in our library. So we picked them out and tested them for TSLP, and we didn't really get any improvement on TSLP activity. We got close in these and other compounds, but they were all shown, at least the compounds shown here, they were all blockers of SYK. So in spite of being active inhibitors or potent inhibitors of SYK kinase, they were not increasing their activity down-regulating TSLP production. So, interestingly, some of them, represented here by compound 11, lost their TSLP activity, and we didn't progress any further with these compounds, but what we obtained was a compound that was less active, and so we think that this would be a good starting point to profile and to look at what was the reason why these compounds, being so close to compound 4, lost activity in TSLP assays. So in spite of having a negative result from this optimization, which means we didn't get any more potent compound in terms of TSLP, we can extract information from those compounds losing activity, so we can do SAR and try to pinpoint what is the activity, or one of the activities that was responsible for this loss. I will show you an example also what we did with external compounds of wabaine and compound 6. We didn't get any improvement with norcodazole in terms of potency. So we did obtain indeed more potent compounds represented by 15 and compound 16 for a wabaine and compound 6. And again, this is very interesting because it opens up the possibility of doing both additional optimization. For example, remember this compound number 6 is associated to apoptosis. So we have the opportunity to look at apoptosis induction in these more potent compounds and try to separate the apoptosis activity that we are seeing from the TSLP activity. So all the things that we see in this phenotypic hits, cytotoxicity, induction of apoptosis, blocking a channel, that is something we may not want, we have an opportunity to separate them from our main phenotype during optimization. So again, these compounds 15 and 16, could be a further profile and really in parallel with the original compounds of wabaine and 6, and really try to find out what is really responsible for this strong improvement in potency. So this is just to highlight, to summarize how I have tried to show you how we have used both target and phenotypic-based optimization. We can combine that to either generate information that may be useful for example, generate a new program, or to be used as a means to optimize compounds in parallel with a phenotypic-based assay, or alone, if we decide that this activity that we have found really is the activity that is responsible for the phenotype. This is just to summarize what we consider our chemical starting points. So to the left, the P38 inhibitors, which I would say, having that high degree of optimization, would be good candidates for having this high degree of optimization. Compounds 2 and 3, at least compound 2 would be a candidate for target identification, because whatever we get is not going to be very complicated to sort out as compared to other less optimized compounds. Compound number 4, which is the compound that we have profiled in depth, also we can extract information from the SAR that we can perform with this compound, and maybe be able to separate some of the undesired activities in the form of cytotoxicity, for example. And for compound 6, again, since we have had the chance to get a higher activity for wabaine and compound 6, compounds 15 and 16 represent opportunities to do additional profiling and go in depth into additional information in terms of biology. So biological starting points are obviously very related, and this refer to, going back to the beginning of my talk, to what is behind this activity of compound 1 upregulating TSLP production. This would be very interesting for us, and I think for people that may be studying biology of TSLP. P38 selective hits, again, can help really be helpful to characterize the true role of P38 in this context, and maybe uncover other activities that may be contributing or synergizing with P38 to downregulate TSLP. mTOR, obviously, we think it may be directly related with TSLP, but again, as for P38, other activities are probably contributing to the phenotype, in this case, in compound number 4. And I also refer to profiling of compounds 15 and 16 already. So the take-home conclusions and future prospects. We have performed a phenotypic screen. We're using poly-IC-IL4 stimulated TSLP production in human bronchial epithelial cells. We have identified several chemical and biological starting points, which we believe can be of use for further optimization or for further exploitation by people interested in scientists interested in working in TSLP biology. Our results suggest a direct role of mTOR pathway in the control of TSLP production in these cells, while P38 and JAK appear to play, at least in this context, a partial role, but they may play a role, but there are probably also contributions from other targets. So, and overall, these results indicate that inhibition of TSLP production in these cells appears to be the result of a combination of activities, which is something that we were expecting, in fact, but it's something that we have to sort out using these profiling tools, or we have tried to sort out using these profiling tools. So I think, this work shows how, going back to one of the concepts I introduced at the beginning, how target and phenotypic-based activity are not antagonistic approaches. On the contrary, they're complementary approaches which are really interconnected and can be used in combination along the drug discovery process. So going to the final acknowledgements. I mentioned at the beginning that this has been published this last January, so I invite you to look at the paper, which is shown here at the bottom of this slide. And I obviously would like to thank all the people that was involved in this work. Adela in the screening group, Vicente, molecular biology, Rosa, cell biology, Sonia, Estrella, Julia, Antolin, Stefan, Miriam, Dulos, Ragnish, Paul. Some of them have gone to other companies, to other groups, but they really did each of them contribute strongly to this work, together with additional contributions from other people, including the availability of lab-2 cells for the sick assays, which were provided by Dr. Kirschenbaum from the National Institutes of Health. And I stop here, and I thank you very much for listening.
Thank you, Arsenio. Now it's time for our question and answer session, where Arsenio will answer your questions. And don't forget, you can still submit questions using the Ask a Question section situated below the player. So let's move to our first question, and that is, does this technique predict a potential toxicity of the selected molecule based on identified relevant activities of the selected molecule? Arsenio?
Okay, thanks for the question. Yes, this is a classical question that we have, and I would say that the advantage of these predictive tools is that we can compare the results of our profiling with the compounds in the database, and this may give us a clue on whether our compound is behaving similarly to compounds having potential safety risks. So this is the way I guess we should go to really then after that initial clue of potential similarity to a potential safety issue, then go on to do an assessment of the compound on its own. But I would say it is a first step.
Thank you for that answer. The next question concerns compound 1. Has compound 1, the TSLP production stimulator, been characterized any further? And do you think this would be of any value?
No. We haven't characterized it any further. As you can understand, this was not a priority. But I would very much like that people or the scientific community could take advantage of this structure and maybe use it for additional profiling and try to sort out what is the reason why it is down-regulating, it's up-regulating the production of TSLP in such a robust way. But no, we haven't.
Okay, so was the library enriched in any type of chemistry, kinase inhibitors? Was it sufficiently diverse to take advantage of the potential phenotypic screening?
Well, I don't think so. I think for phenotypic screening, we should really try to access more diverse libraries and take full advantage of the great effort that we put together to run a phenotypic screen. Of course, it was the library we had at that time, but I would say we would probably add more diversity if we were to have the capability to do so in order to access as much biology as possible through the chemistry that we have in our library.
Thank you. We now move on to optimization of compound 4 with a question that runs, how would you proceed with optimization of compound 4? Would you just base it on the TSLP assay? And what other assays would you include, if any?
I think in this case, as in other of the cases I mentioned, we would need to look into the activities that we are seeing as either not desired activities, like cytotoxicity, for example, in endothelial cells for compound 4, and really try to separate those activities from the TSLP, from the improvement in TSLP production. So doing SAR with some of these activities that we have identified through profiling both negative and positive, I think is the key to progress compounds. Later on, we may be able to narrow down a specific target or a key target from that list of 12 targets and then continue that pathway. But again, any of the activities that may not be so desired in our profile, we need to keep them in a screening cascade in order to monitor how it hopefully disappears.
Our next question begins with an observation. Selectivity profiling provides the opportunity to look for selective compounds during optimization. Is that your preferred choice? Would you accept a polypharmacology profile?
I would say we are open at the beginning because we want to capture as much diversity in terms of biology, as much new biology, new opportunities to do original biology at the beginning. But then as we move on with the compound, as we progress with the compound through the process of optimization, I would be happy to have maybe one target defined as the main target of the compound, so that we can have we can focus our resources in really improving that and really making sure that because if we had let's say 5-6 targets that we need to optimize, that we see that that are required for activity, this we could progress that type of compound, but still would be very complex and very cumbersome as we proceed. So I would say I'm open at the beginning, but then I would rather have a more specific, a more selective compound to optimize at the end of the process and hopefully to take that as a candidate.
Thank you for that clarification. Our next question is, was TSLP included in the BioMAP markers panel? And if it wasn't, what was the thinking behind that?
Well, I once asked this question, and the answer was, it's pretty obvious. The BioMAP panel relies on a database with reference compounds, which goes back a few years now. And this database is built on a preset number of readouts. So adding any new readout or additional readout would be informative, but would not be something that could be compared with the reference compounds stored in the database. And that's why it's just not included. So we obviously we can do the assay outside the panel if we are interested in.
Okay, thank you for that. Have you considered using transcriptomics to profile hits at that stage? And do you think this would add any benefit at this early stage?
Transcriptomics provides a lot of information that can be very complex to interpret, and at the same time gives you the opportunity to access in a non-biased way a lot of information and a lot of the effects that the compound may be having on your cellular context. So I would say yes, but again, with a more optimized compound. For example, doing transcriptomics with the p38 selective compounds is probably easier to interpret than taking a non-selective compound and trying to interpret the transcriptomics or the changes in mRNA expression that it's causing. And so I think it's very useful, very potent, but needs to be done with selective compounds.
Two questions bound together here. Do you think it's possible to capture disruption of non-protein related intracellular events, like, for example, RNA functional activities, using this type of approach? And also, could this be behind the apparent impossibility to clearly identify the targets in some cases?
Yes, indeed. I think, and in fact, this is when I mentioned before opportunities accessing new biology, I was thinking about this. So we should be looking not only to the conventional disruption of protein-protein interactions and enzymatic activity, we should be looking into anything that is going on inside the cells that may be relevant for the biology of the readout or the phenotypic readout that we want to link to disease. So if we have this opportunity to capture mRNA structural or RNA structural effects or anything other than conventional protein or biochemical activities, I think that would be great. And I definitely believe that probably we would find that in any of the of these hits that we look at and where we don't seem to be finding the target. So definitely yes.
Thank you for that. One delegate wants to know, could CPD4 be a potent mTOR inhibitor and your mTOR kinase assay format just can't show the true potency? Would you agree with that?
I'm sorry, could you repeat the question?
Yes. Could CPD4 be a potent mTOR inhibitor and your mTOR kinase assay format cannot show the true potency? Would you agree with that assessment?
I'm not sure I can answer that question. Maybe yes. Maybe yes, it would be an assay effect, but I'm not sure I know the answer to that.
Fair enough. Let's move on. For BioMAP, would it be feasible to recover the cells used in the assay panel for transcriptomics analysis later on? Do you think that would be useful?
Of course, yes. Like I said, if we had a compound that is optimized enough, but probably would be limited by the quantities of RNA that could be captured, so obtained from these assays. So probably we would need to set up a parallel assay mimicking the same conditions to do that. But I don't know. I guess this is something that people in Discoverex running the assay could look at.
Okay. Finally, why did BioMAP find a match in its database and Bioprint didn't? Does this make sense to you?
Yes. I guess it's because we were looking into both databases with a compound that is essentially a kinase inhibitor and or derives from a kinase inhibition chemistry. And this is something that's probably more relevant in the context of the cellular assays that we are looking at in BioMAP. and not so much in the Bioprint platform, where most of the assays are non-kinase related, and these assays try to cover more general biology. So probably it has to do with the selective nature of the compound and also its kinase origin.
Thank you for that. Unfortunately, that's all we have time for today. Any unanswered questions will be responded to by email. So please join me in thanking Arsenio Nueda for his compelling presentation and wide-ranging answers. I'm Mike Stones. On behalf of Drug Target Review and Eurofins Pharma Discovery Services, I'd like to thank you all for attending today's webinar. We hope to see you again soon. Goodbye.